going on? Okay, guys, good morning, everybody. What's going on this month? So today we're going to talk about last week we talked about estimation methods for VAR. So today we're going to talk about estimation methods for expected shortfall. But is it going to stop or what? Is it an alarm? No. All right, let's begin. Okay, the first of all, I will talk about parametric estimation methods for expected shortfall. The first one is based on the normal distribution, and we know from about 2 weeks ago. I showed you for the normal distribution, the expected shortfall is given by this formula. And you should know from the statistical methods course, the MLEs was mu and sigma are this and this, right? And hence the MLE for the expected shortfall is given by this, right? So that's the first method. The second method is uniform distribution method. Right here, from 2 weeks ago, you know the formula for the expected shortfall is this. And you should know from statistical methods, the MLEs for A and B are the smallest and the largest data point. And so hence the MLE for expected shortfall is given by this. And it can be shown that this is asymptotically unbiased and consistent. I will try to show that later today. Okay. And method number 3 is this. We assume that the losses are from a power function distribution, which has this CDF. So the VAR is given by this formula. The expected shortfall is given by this formula, right? And we know from last week that the MLE for A is this one, and hence the MLE for expected shortfall is this one, right? That's expected shortfall. Number 4, so that's number 3. Number 4 is the viable distribution method. I think I did this as an example in the tutorial last week or the week before last week. And for this CDF, the formula for the expected shortfall is given by this, right? All right, this is the formula for the expected shortfall. And there are 2 parameters, theta and beta. And it can be shown, I don't expect you to know that. I don't expect you to know this, that the estimators for theta and beta are the solutions, are the simultaneous solutions of these 2 equations, where x bar is the sample mean and s squared is the unbiased version of the sample variance. So hence the estimator for ES is given by this. So those are there are 4. So these are the 4 parametric estimation methods. I need to speak louder because of the background noise today. I think there's some kind of a fire alarm going on in the department in Kilburn. All right, now let's go to this non-parametric estimation methods, right? And the first of them is known as the historical methods. Now, remember last week also we talked about the historical methods, but that was historical methods for estimating war. Now, what you see here is the historical methods for estimating ES, right? So this is slightly different. So what you do is, again, you arrange the data from the smallest to the largest. So this is the smallest, and this is the largest. And then you compute the expected shortfall as this, where this notation, you might have seen this before, denotes the largest integer less than or equal to x. Oh, thank God. Okay. All right, so this notation denotes the largest integer less than or equal to x. For example, in brackets of 6.1 is 6, in brackets of 5.9 is 5, in brackets of 0.5 is 0. So this is the formula you need to use in order to estimate expected shortfall by the historical method. So I've done some example here, like if you look at this example, so you have these losses, right? And so the first thing you need to do is to arrange the losses in increasing orders. So this is the smallest and this is the largest. So if you want to find expected shortfall at 0.2, first you will compute n times p, which is, sorry, it should be n times p is, n is what? N in this case is 6, right? So 6 is the number of data points. 6 times 0.2 is 1.2, right? So it's 1.2 here, 1.2 here of this. So the bracket of 1.2 is 1. So you sum from 1 to 1 of this, which is minus 10. So this is the same example with p equal to 0.9. So if p is 0.9, then n times 0.9 is 5.4, right? Okay, so you have a bracket of 5.4 and I from 1 to brackets of 5.4, which is 5, right? So you get this answer here, minus 8 divided by 5. So that's the historical methods. It's easy to use, guys. Are you guys okay in the Zoom? Hello, guys. If you have questions, use the chat room. Okay. All right, that's the first non-parametric method. The second non-parametric method is the Bootstrap method. Again, this is similar to the Bootstrap method that we talked about last week. So what you do is you have the original data, you compute the empirical CDF, which is given by this. I showed you a picture of the empirical CDF last week. It's like a staircase, right? And you simulate B independent random samples from F hat, which is this. There are functions in the R software to do this, right? And for each of the B samples, you compute the expected shortfall by the historical method. So you get these estimates, this many estimates, depending on what B is. So if B is 100, you get 100 estimates. And finally, you compute the mean or the median of the estimates in the previous step, right? So it takes either the mean or the median, right? So that's the Bootstrap method. And the next method is the Jackknife method. So again, this is very similar to the Jackknife method I talked about last week. So the first step is to compute the expected shortfall by the historical method for this. So as you can see, what I've done here is it's the same as the original data, but I removed the first data point. Okay. And the second step, you do the same thing, but remove the second data point. And the final step, you do the same thing, but you remove the nth data point. All right. So every time you remove a single data point and estimate the expected shortfall by the historical method. Okay. So after all these steps, hi Veronica. It's okay. Oh, you waited outside.
Yeah.
Lucky we didn't go. Yes. All right, and the very final step is to compute the expected shortfall as the mean or the median of these n different estimates, right? Okay, so that's Jackknife method, and the next one is number 4, is the kernel method. So this is again similar to the kernel method that I talked about last week this time. So you have the losses, and the formula for the kernel estimator for expected shortfall is given by, I know it's a complicated expression, but don't worry, I will explain what each of these things is. Q hat is given by this formula, where these are the data in the arranged increasing order, right? And KH is given by this formula, where H is the bandwidth. As I explained last week, H controls the smoothness of the estimator. If H is small, it will be zigzaggy, like meaning that it's not so smooth. Where if H becomes larger and larger, it will become more and more smooth, right? Okay, and AH, AH, the AH here is given by this formula, where A is the integral of the kernel function K. K is the kernel function, and is usually taken as the PDF of the standard. I'm sure you remember this. This is the PDF of the standard normal distribution. So K is usually taken to be the standard normal PDF. And A is just the integral of K, of the kernel PDF. And AH is defined as A at U divided by H, where H is the bandwidth. And KH is defined in this way, where again, H is the bandwidth. Okay. All right, guys. So although it looks pretty complicated, it's not difficult to code. I think there are some, if I'm not mistaken, there is some functions in R that can compute this formula for you. So you don't need to, in the exam, no, I don't think I will ask you this. It's really complicated. In the exam, I will not ask you this, but I think like for those of you who want to apply this in practice, I think there is a function in R that can compute this. So don't worry. So that's method number 4. And method number 5 is known as the Richardson method. Actually, Richardson was a professor at the University of Manchester. You can see his photo at the ground floor of the Alan Turing building. You might, I mean, you should go to one of the lecture rooms on the ground floor of ATB. You will see his photo there. Maybe you have already seen it. I don't know. And you might have seen it. His photo is there. Well, he was a professor a long time ago. He's not alive. He's not, obviously, he's not alive now. So anyway, so this method is named after him. And so it has quite a few steps. The first step is to compute the empirical CDF, which I showed you how to do. I mean, I talked about this before at least 2 times. And the second step is to simulate a random sample x1 to xn. Here, n need not be the same as little n. Little n is the number of data or the number of losses you have. Capital N can be anything. It doesn't need to be the same as little n, right? So you simulate this from f hat. F hat is the empirical CDF, right? And then you use the historical method to estimate the expected shortfall for this data that you simulated. That's step number 3. Step number 4 is to repeat step number 2 and 3 1,000 times. So you're gonna repeat these 2 steps 1,000 times. So each time you repeat, you will get an estimate for ES, right? So repeat 1,000 times, you get 1,000 different estimates for expected shortfall, right? Okay, so now in step 5, you see what I've done is to take the average. It will take the average of the 1,000 estimates for expected shortfall that we got. Okay, and I'm going to call that little mn, where n is once again need not be the same as little n, capital N, not little n, right? Okay, all right. And the next step, so that's step number 5. There's a question. It really doesn't matter, Muhammad. It can be greater than n, it can be less than n, or it can even be equal to n. So they're not really related, capital N or little n, they're not really related. Okay, right, okay. All right, then the next step, that is step number 6, is this one. You define Sj as m subscript n subscript j. So this is like 3 levels, okay? For j from 1 to k plus 1, for some values n1, n2 to nk plus 1. So for example, you should take k to be 1, you can take n1 to be 100 and n2 to be 1,000. So what you do is you pick some values for, you pick a value for k, right? You pick a value for k, and then you pick some values for n1, n2 up to nk plus 1. So it could be like 100, 200 up to say 1,000, all right? Or it could be say 1,000, 2,000 up to say 10,000. That really doesn't matter. Like you pick some values, you pick a value for k, and you pick some values for n1 to n2 to n1, n2 up to nk plus 1, right? And then you compute this, right, using the method, the previous steps. And the very final step is to define expected shortfall as the ratio of these 2 determinants. So what you have here is a determinant, and what you have here is a determinant, right? So here you have, let me think, 1, 2, all right, so it's a k plus 1. So this matrix is k plus 1 times k plus 1, right? And so is this one. This matrix is also k plus 1 times k plus 1, I mean in dimensions. So for example, if k is equal to, if you choose k to be 1, then you will have a 2 by 2 matrix. This will be a 2 by 2 matrix, and this will be a 2 by 2 matrix, right? And you take the determinant of those matrices and take the ratio. Okay. Okay, is that clearer now or no? If it's not clear, let me know, guys. I'll try to explain further. So that's the final, the last of the non-parametric methods for computing expected shortfall. The next one is the semi-parametric estimation methods for expected shortfall. So this is the first one. So suppose you have losses x1, x2, etc., and let RT denote the return. So RT is defined as the difference between the losses, right? Now suppose RT is heavy tail process. So this is kind of what I have in the red box is the definition of a heavy tail process. A process is said to be heavy tail if the probability that RT greater than minus X behaves, this sign here, by the way, if you're not familiar, this means behaves as, right? It means behaves as. So this probability behaves as this, as X goes to infinity, where alpha is positive, and L is a function that satisfies this. Actually, the function a function, if a function satisfies this condition, it is said to be slowly varying, slowly V-A-R-Y-I-N-G, varying. Okay. All right. So this is basically a definition of a heavy tail process. So suppose RT satisfies this, then go to the next page. So if RT is heavy tail, then the estimator for expected shortfall is given by this complicated. Again, my apologies for the complicated form of this. Ln P is the integer part of this, right? N times P plus 0.05. Alpha subscript L comma N is given by this, right? So L must be a number between, so L, in this case, L must be a number between 1 and N, right? Okay. And these R1 to Rn are the sorted values of the returns, right? In other words, so this is the smallest of the returns. This is the smallest of the returns, and this is the largest of the returns. Okay. So this is, and here, although it looks pretty complicated, I know it looks horrendous, but here alpha, you should read this as alpha subscript. There are two subscripts here. The first subscript is L subscript N comma P, which is defined by this, right? And the second subscript is N. N is the number of data or number of losses, right? You follow me? Okay. So there are, you should read this as alpha subscript with two subscripts, this being the first subscript, this being the second subscript, right? Okay. And this is the definition of alpha. And here, this is R with subscript L. So again, this is subscript. This is a subscript for R. Right, the subscript is L subscript N comma P, right? And the integration here is with respect to Q. Q is the variable of integration, and it goes from 0 to P. And then you, after taking the integration and dividing by P, and then you take away 1, right? That will give you the estimator for ES. Once again, I'm sorry for the complicated form, but as you know, some mathematics are complicated. I mean, no. Actually, for the exam, I mean, you should go to the course website. I've already given you a list of formulas you need to remember. Did you check or not? Not yet. Yeah, by the way, for the in-class test, I sent you guys an email last week. Did you read my email? The in-class test will be on the, well, you will have one full day to answer. I mean, I think it will open on the 16th of December, which is a Thursday, yeah, at 1 p.m. And it will close on 17th of December, which is a Friday at 1 p.m. So you have 24 hours to work on the question and upload it to Blackboard. Okay. Yeah. Okay. All right. So, all right. Let's get back to here. That's the first of. This is method 1 of semi-parametric methods. Method 2 of semi-parametric methods is a simpler one. It's simply given by this, right? This is, should read like this: F inverse of the empirical CDF plus this term here, where F hat denotes the empirical CDF and of RT, and gamma hat is given by this formula here, where K is a number between 1 and N, right? Okay, guys, any questions? So those are the two semi-parametric methods for estimating expected shortfall. Any questions so far, guys? Please let me know on the Zoom. You guys have any questions? Okay, all right. So let me do some, last week I tried to finish an example. I did not have, I ran out of time. So let me see if I can try to finish it today. At least, this is example 1. All right. Suppose you have data from normal with these parameters, then we know that the expected shortfall is given by the following. Okay, this is, as I already shown you, this is the formula for the estimator for expected shortfall. Now, what I want to show is I want to find the bias and MSC. All right. All right, let's start with the bias first. To find the bias, okay, and this is gonna be the expected value of yeah, this is the expected value of this minus the formula for the this is the formula for the expected shortfall, right? Okay, now I'm gonna, if you don't follow me, please feel free to say so. All right. Are you with me? Are you okay following me? Right. Now I'm gonna X bar is the sample mean, right? So you can write it as the expected value of 1 over n times the minus mu, right? Now I combine these two to write this. Now you may know from your statistical methods course that this guy here, or some other course that you took in your previous studies, that this guy has the following distribution: sigma squared times chi squared n minus 1, right? Okay. Now, if you take the expectation inside, you get there's a sigma squared here, right? You can, so the square root of sigma squared is sigma. So you can pull it outside. This is a common factor. So in brackets, you have 1 over root of n times the expectation of the square root of a chi-squared variable minus 1 multiplied by okay, right? Okay, now we know that for a normal distribution, the expectation of xi is mu Now it can be shown, I don't expect you to know this, but it can be shown that the expected value of the square root of a chi-squared variable is given by the following. I mean, I don't expect you to know, to be able to prove this, but if you can, that's great. Okay. Times okay. So you guys following me or no? Let me know if you can't. Now, what you have here is n times mu, right? Because sum of mu is n times mu. So n times mu divided by mu is mu. So you have mu minus mu, which they should cancel. So times Okay. Are you with me? Yeah. Or are you lost? Let me know if you can't follow me, please let me know. Yeah, so these two guys cancel. So what you have is sigma by P all right, okay, and it can be shown that as n goes to infinity, and again, I don't expect you to know this. I mean, I don't expect you to be able to prove this, but it can be proved that this expression here approaches zero as n approaches infinity. So which implies that the estimator is asymptotically unbiased. Okay. Right. Okay. Now that's only one part of the question. The second part of the question is to show that to find the MSC, or MSC means mean squared error, if you don't know what that is, but MSC of this guy here, right? Now, let me show you. I hope I have the time. Are you okay with this, guys? Can I take it away? Yeah, okay. All right, so to find we have this estimator ESP equal to this, right? The estimator is equal to this. So to find the MSC of the estimator, I'm going to use a well-known fact. You might have learned this in your in statistical methods or some other course that you took in your undergraduate degree. That the MSC is equal to the variance plus the square of the bias. That's a well-known fact. So we know what we already found what the bias is, right? So all we need to work out is the variance. So we need to find the variance of the estimator of expected shortfall, right? All right, which is equal to the variance. It's not to be confused with VAR, okay? So it's easy to confuse the two. The VAR and the variance, they look similar. Okay. Right. Now, I don't know whether you know that this is again from statistical methods, that X bar and this guy are independent. If you have a data from normal distribution, these two that's a well-known fact, right? You should remember from stat methods. So because they are independent, you can write this as follows. You can write this as the variance of X bar plus 1 over P squared times 1 over M times the variance of the square root of right times the square of, so excuse me for the complicated formula, but this is sometimes things are complicated. All right, so okay, now variance of x bar is simply the variance of the sample mean, which is, I'm sure all of you know, is this. Okay, and here I'm gonna put p squared. It became p squared because p is a constant and n is a constant. So the root of n becomes n, p becomes p squared, right? And also this is a constant, so this becomes squared, right? Okay, so you have variance of the square root of sigma squared, chi squared, n minus 1, which is again another result that you should know from your undergraduate degrees. Okay, you with me, guys? Right, now the next thing is to take the variance inside. You get 1 over n squared times the sum 1 to n of the variance of xi. Yeah, and here you can sigma, here you have, if you pull it outside, it becomes sigma squared, right? So it becomes sigma squared divided by p squared n times the variance of the square root of chi squared n minus 1 multiplied by yeah, and the variance of xi is variance is sigma squared, right? So it's gonna be 1 over n squared times n sigma squared, because you're summing a constant from 1 to n, so it becomes n sigma squared. Now again, I don't expect you to know this, but it can be shown that the variance of chi squared of a square root of a chi squared variable is the following. Okay. I'm sorry once again. Well, it looks so complicated, but I'll show you what this reduces to. Okay, and okay, so here we are. So this, from this to this is some mathematics you don't need to know really. Okay, so you have sigma squared by n, which is a common factor. So you have 1 divided by 1 over p squared, right? Then Okay, this still looks complicated. But all right, so this is the final form for the variance of the estimator for ES, right? Now, some mathematics, after some more mathematics, it can be shown that this, as n goes to infinity, this goes to 0, right? Again, I don't expect you to be able to know how to show that, but if you can show that this actually goes, if you can show that, that's great, right? All right. Okay, so what we have shown is that the variance of the estimator for ES approaches to 0 as n goes to infinity. And we also showed earlier that the bias also goes to 0 as n goes to infinity. All right, so going back to this formula here, which I wrote earlier, right, that the MSC is the variance plus the square of the bias. What you can conclude is the following. So we have shown that hence the MSC of the expected shortfall, right, approaches 0 as n goes to infinity. Hence, the expected shortfall is consistent. So it's consistent. Remember, the definition of consistency is that an estimator is said to be consistent if the mean squared error approaches 0 as n goes to infinity. All right, I know it's a I wouldn't ask a question like this in the exam, but it'll be too much for you because it's a lot of math. Yeah, but maybe a simpler one, similar to this, maybe with simpler mathematics. Let me ask you. Yeah. Okay. All right, guys. Any questions, guys? You guys okay? By the way, I will mark all the quiz 6s you have submitted. I have already marked some of them. They look okay. I'll mark them and let you have them by later today. Yeah, so you should know. Okay, so you should receive an email from me this afternoon or this evening, giving the mark and the feedback. All right, guys, have a good day, and I'll see you on Friday. All right, we have a tutorial on Friday, the usual time. Please try to have a look at the questions before you come to the tutorial.